All right, so buckle up, everyone, because today's deep dive is going to get uh, a little out there.
Oh, yeah.
Yeah, we're talking about something called the Fibonacci theory.
Okay, I'm intrigued. Fibonacci theory, you say?
Uh-huh. And it's basically trying to connect the structure of DNA, the stuff that makes us, to the entire universe
The whole universe, wow.
using fractals.
Okay, now that's a pretty big leap.
Right.
So where'd you even come across this? Sounds wild.
Well, we've got this paper, Fibonacci theory, DNA, fractals, and the SMF RVS field.
SMFRVS.
Yeah, that's by L.S. Larkey.
Okay.
So we're basically diving into the mind of theoretical astrophysicists with this one.
All right, well, let's hear it. What's this SMFRVS all about?
Yeah, what is that?
Well, SMF stands for subtle magnetic field, and RVS is relative vacuum of space.
Okay.
And they're theoretical fields. Think of them kind of like an alternative to how we usually think about gravity.
Okay, so instead of gravity pulling things together, it's more like these SMF and RVS are pushing things.
Exactly. It's what Larkey calls push-based synergy.
Push-based synergy, huh?
Yeah, it's a mouthful. The paper gets pretty heavy into the math to describe all of it, tons of
I
equations.
guess it's got to have those equations.
But the main idea is that this push is what shapes everything from tiny particles all the way up to galaxies.
Okay, hold on, let me get this straight. I'm picturing like a cosmic mosh pit with everything getting shoved around by this invisible force.
Yeah, kind of.
But where do the fractals fit in?
Well, you know how a snowflake has that intricate pattern that repeats itself at different scales?
Yeah, like a tiny part of the snowflake looks like the whole snowflake, right?
Exactly. That's what we call fractal invariance, the same basic shape at different sizes.
Okay, I'm with you.
So Larkey's theory says this SMF-RVS interaction creates these stable points, kind of like nodes where things can settle across all those different scales.
So you're saying the same force could be behind, like, the structure of an atom and the way a whole solar system is laid out.
That's the idea, yeah.
Wow, okay. My mind is kind of blown right now.
It's a big concept, for sure. And it goes even further, connecting these fractal nodes to, well, the elements that make up life as we know it.
Okay, now you've really got me hooked. How do we go from giant cosmic forces to the stuff that makes up, us?
It comes down to something called magic number elements. These are atoms with specific numbers of protons that are super stable.
Like what?
Oxygen, nitrogen, phosphorus, stuff like that.
Right.
Larkey sees these elements as being directly influenced by those stable nodes in the SMF-RVS field.
So those elements, the ones that are super important for life, they're stable and therefore abundant because of the
Yeah.
connection to this cosmic push.
Exactly. And then there's carbon. Now, carbon isn't technically a magic number element, but it's close. It's got 6 protons.
6 protons.
Which puts it near a stable node, but not directly on it.
So carbon is like almost magic, but not quite. What does that even mean for something like DNA?
That near magic status is actually key. Since it's a little off-center, carbon has this unique balance, stability, but also flexibility.
Okay.
See, the magic number elements, they're super stable, yeah, but not very reactive. They don't bond easily with other things.
Right.
But carbon can form tons of different bonds, and that's kind of important for, building complex things like life.
Ah, so carbon's got that Goldilocks thing going on. Not too stable, not too reactive. Just right for building the molecules that life needs.
Exactly.
Okay, so carbon's the MVP. Got it.
Pretty much. But where DNA fits into all of this, that's where things get really, really interesting.
Okay, lay it on me.
Larkey's theory proposes that the shape of DNA, that famous double helix, it isn't random. He thinks it's actually guided by this SMF-RVS field and those fractal patterns we were talking about.
Wait, so you mean the shape of DNA is like a tiny little echo of the whole universe?
That's the heart of the Fibonacci theory.
What?
Just like planets settle into stable orbits around a star because of gravity, DNA might fold into its specific shape because of this cosmic push.
So instead of just being random, our DNA is like this perfectly choreographed dance guided by forces across the entire universe.
Pretty much.
That's mind-boggling.
Yeah, it's a big concept. And the paper actually lays out a mathematical model to try and explain it all. And this connection between DNA folding and this universal push.
So there are equations that suggest our DNA might be shaped by the same forces that affect galaxies.
That's what Larkey is proposing, yeah.
It's a pretty huge leap.
It is a pretty big leap. But that's what's so fascinating about this whole Fibonacci theory. It connects things we normally wouldn't even think to put together.
Well, you've definitely got me curious. What other implications does this theory have? I mean, if our very DNA is shaped by the universe, where does that lead us?
Well, that's the question, isn't it? And there are a lot of places we could go from here. If our DNA is shaped by these cosmic forces, then maybe, just maybe, evolution isn't as random as we've always thought.
Well, hold on. Now that's a thought. I mean, we always think of evolution as random mutations and natural selection, survival of the fittest.
Right, right.
But are you saying this SMF-RVS field could be, like, guiding the process?
It's a possibility, yeah. Remember those stable nodes we were talking about? Those points of stability created by the SMF-RVS field?
Yeah.
Maybe evolution is less about random changes and more about finding those nodes, like DNA is drawn towards those stable configurations.
So instead of blindly stumbling around, evolution is more like a guided search. Like there are these cosmic signposts saying, hey, over here, this way leads to a stable structure.
That's a great way to put it, yeah. And if that's the case, well, it could help explain some of the patterns we see in nature.
Like what kind of patterns?
Think about convergent evolution, when totally different species end up evolving similar traits because they're adapting to similar environments.
Okay. Yeah.
Like dolphins and sharks, for example. One's a mammal, one's a fish. But they both have that streamlined body shape perfect for moving through water.
Or like birds and bats,
Right.
right. They both have wings, even though they evolved along completely different branches of that evolutionary tree.
Exactly. So maybe those similar traits are a result of DNA being pushed towards similar solutions by this underlying SMF-RVS field.
So the same force that shapes galaxies could also be shaping the evolution of life on Earth.
That's what the theory is suggesting, yeah.
That's a pretty profound idea.
It is.
But okay, let's be real for a second. This Fibonacci theory, it's pretty out there, isn't it?
It's definitely a bold theory, yeah.
I mean, how much evidence is there to actually support all of this?
Honestly, it's still very speculative at this point. There's a lot more research needed to test whether it holds up. The mathematical model Larkey presents is intriguing, but it needs to be tested rigorously.
Right.
And remember, we're still talking about a theoretical field here, this SMF-RVS thing. That's not a proven concept either.
So it's more of a thought experiment at this point, a new way of looking at things, even if we don't have all the answers yet.
Exactly. It's like a new lens we can use to view the universe and our place in it. It challenges us to consider the possibility of these deep connections, hidden patterns, and forces that we might not even be aware of yet.
I like a new lens. It's a good reminder that there's still so much mystery out there, Even if this Fibonacci theory turns out to be wrong, it still sparked this amazing conversation and made us think about things in a whole new way.
Absolutely. And that's what science is all about: questioning, exploring, pushing the boundaries of what we know. Sometimes even being wrong can lead to new insights and discoveries.
Well said. This whole deep dive has been an incredible journey so far. We've gone from the structure of DNA to the vastness of the universe, and now we're talking about the very nature of evolution.
Yeah, it's pretty amazing.
It's amazing how one theory can connect so many different ideas, ideas that seem totally separate at first.
It really shows the power of human curiosity and that drive to understand the world around us. And even though the Fibonacci theory is still in its early stages, it hints at the possibility of some truly groundbreaking discoveries in the future.
I'm definitely going to be following this theory closely. Who knows what other incredible insights it might unlock as scientists continue to explore it.
It's an exciting prospect for sure. It speaks to the beauty of science, that journey of discovery that never truly ends.
Yeah, there's always more to learn.
Always new questions to ask, new mysteries to unravel.
This whole conversation has been so stimulating. But before we get too lost in the big picture, there's one more aspect of the theory I'd love to unpack.
All right, what's that?
We've talked a lot about carbon being this near magic element.
Yeah.
But how does that actually play out at the molecular level? How does this SMF-RVS field influence the way carbon behaves in DNA?
Now we're getting into the nitty-gritty details of how this theory might actually work. And it all comes down to how the SMF-RVS field interacts with those tiny little electrons that hold DNA together.
Okay, we're going subatomic again.
Yeah.
Take me back to high school chemistry for a second. Remind me how electrons and bonding work.
Sure. So atoms, the building blocks of everything, are made up of a nucleus with protons and neutrons, and then electrons orbiting around that nucleus. Those electrons are organized into shells, and the outermost shell is called the valence shell.
Okay.
That's the shell that's involved in bonding with other atoms.
Right. And atoms can share electrons to form bonds, which is how we get molecules. It's like they're holding hands to stay connected or something.
Exactly. Now, what Larkey proposes is that this SMF-RVS field can actually influence the energy levels of those electrons, particularly the ones in carbon's valence shell.
Wait, so this cosmic push is messing with those tiny little electrons in carbon. How does that even work?
Think of it like this. The SMF-RVS field creates these subtle variations in energy throughout space. It's like a cosmic energy landscape with peaks and valleys, and those variations can affect how electrons occupy their orbitals within an atom.
Okay, so it's like carbon is surfing those energy waves created by the SMF-RVS field.
Yeah, that's a great analogy. And because carbon is near magic, remember, it's close to a stable node but not quite on it, its electrons experience this kind of push and pull, this energetic tug of war.
So carbon is in this sweet spot where it's sensitive to those energy variations.
Exactly. And that affects how it shares its electrons with other atoms,
Yeah.
influencing the stability and the geometry of the bonds it forms.
So this cosmic push, these energy waves, are actually shaping the way carbon links up with other atoms to form DNA.
Yeah.
It's like the SMF-RVS field is whispering instructions to the DNA molecule saying, fold this way, twist that way.
That's a beautiful way to put it. The theory suggests that the SMF-RVS field, through its influence on carbon's electrons, is actually encouraging the formation of that double helix structure we all know.
That is just wild.
Yeah.
And it all stems from carbon's unique position as that near magic element.
Right.
If it were perfectly stable, just sitting right on one of those nodes, it probably wouldn't be as responsive to the field.
Exactly. It's that slight imperfection in carbon stability that allows for all the complexity and elegance we see in DNA.
We've gone from the vastness of the cosmos to the tiny dance of electrons, and it all seems to be connected by this idea of a cosmic push that's shaping the very fabric of life.
It's pretty incredible, isn't it?
It's mind-blowing.
It really highlights how interconnected everything in the universe is. Even the smallest particles are influenced by forces that extend way beyond anything we can easily perceive.
It makes you realize just how much we don't know about the universe and our place in it.
It really does.
But it's also incredibly inspiring. Makes me want to go out and explore, look for those hidden patterns and connections that might be weaving everything together.
That's the beauty of science. It sparks our curiosity, opens our minds to new possibilities, and keeps us asking questions.
This deep dive into the Fibonacci theory has definitely been one for the books. We've explored some truly mind-bending concepts, from the cosmic scale down to the molecular level.
It's been quite a journey.
And even though the theory itself is still just speculative, it's opened up this whole new world of possibilities.
Yeah, it has.
But before we wrap things up, I'm still kind of curious about the nitty-gritty details of how this actually works.
Okay.
How does the SMF-RVS field interact with carbon at the molecular level to influence the shape of DNA? I mean, how does that actually happen?
That's a great question, and it takes us even deeper into the heart of this theory. So we're talking about those energy variations again, those peaks and valleys in the cosmic energy landscape created by the SMF-RVS field. Yeah. And how those variations could actually affect the way carbon shares its electrons with other atoms,
Okay.
influencing the angles, the distances between them,
So it's not just about stability then, it's about shaping the way those atoms connect, like the geometry of it all.
Exactly, like an invisible sculptor, The SMF-RVS field is nudging those carbon bonds into specific configurations.
Guiding the DNA molecule into its final form.
Yeah, that's the idea.
So the double helix, the blueprint of life itself, could be a direct result of this cosmic influence.
That's the core of the Fibonacci theory.
It suggests that the forces that shape galaxies are also shaping the very molecules that make life possible.
Right.
Pretty profound stuff.
It is.
And if it's true, it raises so many questions about the origins of life, evolution,
It does. If DNA's structure is influenced by this universal field, then maybe life itself is more connected to the cosmos than we ever thought possible.
I mean, we've always said we're made of stardust, but this takes it to a whole new level. It's not just a physical connection to the universe.
Right.
But like we're shaped by its fundamental forces.
Exactly. It's a whole new way of thinking about that relationship between life and the universe. We're not separate from the cosmos, we're expressions of it.
Wow, intricate patterns in the fabric of space and time.
Yeah.
Mind-blowing. But, okay, let's be practical for a minute. Is there any way to actually test this theory? How could we prove that this push is shaping DNA?
Well, it wouldn't be easy. You'd need incredibly precise measurements,
Right.
sophisticated experiments to detect those subtle energy variations, and then see how they affect molecular structure.
So we're talking about pushing the boundaries of science as we know it.
We are. It's like trying to listen to a whisper from the universe itself.
Exactly.
But that's the thrill of science, isn't it? That constant pursuit of knowledge, always pushing those limits.
Always asking, how can we know more?
And who knows, maybe someday we will have the tools and the understanding to really put the Fibonacci theory to the test.
Unlock even more secrets of the universe.
Yeah.
This deep dive has really given me a lot to think about. We've gone from the structure of DNA to the vastness of the universe, and now we're contemplating the very nature of life itself.
It's been quite a journey.
And it all started with this one wild idea.
It highlights how important it is to stay curious, question our assumptions, be open to new possibilities, even if they sound a little crazy at first.
Because that's how we make new discoveries, right?
That's how we expand our understanding of the world around us.
Well said. And on that note, we'll leave our listeners to ponder the Fibonacci theory and its implications.
Okay.
Is our DNA a tiny echo of the universe? Is life itself an intricate pattern woven into the fabric of space-time?
Big questions.
The answers may still be out there waiting to be discovered. Until next time, keep exploring, keep questioning, and keep diving deep into those mysteries of the universe.